Ever wondered why time flies when you're having fun, but drags when you're bored? Could it be possible that time changes based on our perspective? Enter the theory of relativity, a concept that revolutionized our understanding of space, time, and the very laws of physics. It's a little like looking at the world through a kaleidoscope. Your perspective shapes your reality. Now, the theory of relativity is twofold. First, we have special relativity, which deals with objects moving at a constant speed. It tells us that space and time are intertwined into a four-dimensional fabric called space-time. Then, there's general relativity. This is where things get a bit more complex. General relativity deals with objects that are accelerating, particularly due to gravity. It paints a picture of gravity as a curve in the fabric of space-time. Bull. So, even though it may seem like time is slowing down when you're bored, according to the theory of relativity, it's not. But don't worry, things are about to get more interesting. Imagine if you could travel at the speed of light. Would time stand still for you? Such a question leads us into the fascinating realm of Albert Einstein's theory of relativity. This theory, which revolutionized our understanding of space and time, is built on two key ideas. One, that the laws of physics are the same for all observers in uniform motion relative to one another. And two, that the speed of light in a vacuum is the same for all observers, no matter their motion or the motion of the source of light. So let's talk about the speed of light and its significance in this theory. Light travels at an astonishing speed of roughly 186,000 miles per second. That's like circling the Earth 7.5 times in just 1 second. And according to the theory of relativity, this speed is a constant for everyone, regardless of where they are or how fast they are moving. Now let's bring time into the equation. Time, as we understand it, ticks away at a consistent pace. But here's where things get interesting. According to special relativity, if you could travel close to the speed of light, time would appear to slow down for you relative to the rest of the universe. This is not because your watch is malfunctioning or you're in a dream, but due to the very nature of space and time itself. This phenomenon is known as time dilation. The faster you move, the slower time seems to move for you. So if you were on a spaceship traveling at near light speed, time inside the spaceship would pass normally for you. However, if you were to look outside, you might see the rest of the universe in a sort of time lapse with everything moving at a much quicker pace. So if you could somehow travel at the speed of light, you might find that time outside your spaceship appears to move much slower. This is the time dilation concept. Did you know that gravity can bend time and space? This might seem like a line straight out of a science fiction novel, but it's actually a fundamental concept in the theory of general relativity, brought to us by none other than Albert Einstein. He proposed a novel way of understanding gravity, not as a force, but as a curvature of what we call space-time, created by mass and energy. Now let's break that down a bit. Space-time is a four-dimensional framework, combining 3 dimensions of space with 1 dimension of time. When we talk about the curvature of space-time, we're talking about how this framework is bent or warped by mass and energy. Think of a trampoline. When it's empty, the surface is flat, but place a heavy ball in the center and the surface dips. This is similar to how mass and energy cause a curvature in space-time. So, how does this relate to gravity? Well, objects with mass or energy, like our sun, create a curve in space-time. Planets, like Earth, move along this curve. They're not just being pulled by the sun's gravity, they're following the path laid out by the curvature of space-time. This isn't just theoretical either. Experiments have confirmed this concept, like the bending of light from distant stars as it passes our sun. The light isn't merely traveling in a straight line, it's following the curve in space-time created by the sun's mass. This phenomenon, known as gravitational lensing, is one of the many confirmations of Einstein's general theory of relativity. So, the next time you drop something and it falls to the ground, remember that it's not just gravity pulling it down, it's actually following a curve in space-time. Quite a thought to ponder, isn't it?